Okay, when last we met, we were looking at the bromium pentachloride, which is a square pyramidal molecule. And I have put on the group tables some molecules, parts if you want to build one. But we said that was in the C4V group. So, instead of trying to do all of the axes on every single atom, we're just going to look at the bonds. So I like to start out with putting the symmetry operations. So we have E2C4, C2, 2 sigma V, and 2 sigma D. Now, both V and D are vertical mirrors. So what's the difference between them? The D is what we call a dihedral mirror. So the vertical mirror plane is going to cut through as many bonds and atoms as possible. So it's going to go from here to here to here to here, including the C on top. The dihedral is going to cut in between. Okay. So that's how we need to think of them when we're trying to decide whether or not the bonds move. Okay, so if on homework or a quiz or a test, you get the question, write the representation of the BR bonds or of the bonds of a molecule, in this case, BrCl5 in the point group of that molecule, C4V, this is what we're doing right now. So representations, we use gamma, and I like to tell myself what I'm doing here. And the first thing I do is I count how many bonds I have. So on BrCl5, how many bonds do I have? 5. Now, are all of those bonds equivalent to one another? No, because 4 of them are adjacent to a lone pair, and 1 of them is across from a lone pair. So the symmetry tells us if I have something that's a little bit off. So this 1Cl is basically going to have its own kind of vibration. And pretty much as a vibration, what it can do is it can stretch. And that is just going to be totally symmetric. It stretches. That's it. Okay, we don't have any weird combinations. But we'll see where that comes from in just a minute. Okay, so I have 5 bonds. So under the identity, I have 5. And that means I'm going to ultimately end up with 5 different vibrational modes, 5 different ways these bonds can vibrate. All right, so if I have the molecule, I guess if I'm looking at this one, this might be easier to see. If I'm holding it by this chlorine and rotating it 1/4, how many of those bonds stay exactly where they were? 1, right? Just the one that's pointed up. The 4 that are pointed out, they switch with another one. All right. If I do a C2, that's going all the way around, doing a 180. So I'm basically still doing the same rotation, just twice. So it's still just have 1. Okay. My sigma V, I'm going to draw this in pink, is the plane that includes these 2 chlorines, this chlorine, and the bromine. So remember, if the axis or the bond or the symmetry element or the atom is included in that plane, then that means it doesn't move. Okay, so how many bonds do not move when I do a reflection like that? 3 of them, right? And then the ones that are outside are going to reflect into each other. So we have 3 here. Now, if I change this to do the mirror plane that is out like that. Cutting through the between those bonds and just contains the top one, then the ones on the left mirror into the ones on the right. Okay, so how many stay in place? Just one. And one over here. Okay, so that is what is meant by create the representation or write the representation of the bonds.
What is the sigma? What's the D?
D is, it stands for dihedral,
Okay.
but it is another vertical one that goes between bonds. All right, so now what we want to do is we want to reduce the representation. In order to reduce the representation, we need to know the order of the group. So what do I have to do? Add up the coefficients. So 1 plus 2 plus 1 plus 2 plus 2 is going to give me 8. All right. Then what we're going to do is, and you probably want to have out your own character table because I'm not going to write them all out, but what we're going to do is for each representation, we're going to multiply the characters of that representation by these characters and by the coefficients, and then divide by 8. So that's what we mean by reducing.
So what we just did was write the representation, right?
Yeah,
and
we're
now we're reducing.
Yeah.
Okay.
Every representation has an A something that is totally symmetric, and totally symmetric means there's one as every character, which means it's symmetric with respect to everything. So it would be 1, 1, 1, 1, 1. And in this case, it is just A1. All right, we are going to multiply that by the character from our representation and then by the coefficient. Okay, so the first number comes from the character table, what's listed next to A1. So the characters of A1. The middle number comes from our representation, and the last number comes from the coefficients. Now, numeric multiplication is commutative. So if you happen to do the coefficients first and then the others, or if you did A1 last, it doesn't matter. You'll still get the same answer. Okay, I'm just trying to show you where my numbers are coming from. All right, so I have 5 plus 2 plus 1 plus 3 plus 2. And that is going to give me.
So 3 times 2 is 6.
You're right. I was going to say that is not going to be divisible by 8. I was a little bit scared there. So I have 5 plus 2 is 7. 8 plus 8 is 16 divided by 8 tells me 2 of my modes are A1. And that mode is always going to be everything happens at the same time. So we've got one of them that is this vertical chloride that is just going up, and the other one where all the chlorines go out at the same time. Okay. So that's really the one I'm most likely to ask you about on a test or a quiz. We'll talk about how you can picture the other ones as well. All right.
You said it's A1 and not B1.
Because this on the character table is 1, 1, 1, 1, 1.
Oh.
That's where that came. And the fact that those are all ones tells us that it's totally symmetric, meaning the molecule basically doesn't change its shape. It can change its size, but it doesn't change its shape, which means everything's stretching at the same time. All right. So try reducing, well, actually, first let's take a look at A2. before we do any of the math. Now over here, our last two here gave us another 8. In A2, these are all 1, so we're still going to get the 5, the 2, and the 1. But these are going to be negative, right? So I'm going to have 5 plus 2 plus 1 minus 6 minus 2, right? Now, I could go through and multiply that, and if you want to be convinced of it, you can do that. But because everything for the A's and the B's are either positive 1 or negative 1, sometimes you can use this idea to be like, oh, okay, that means those will cancel out. So the 1, 1, 1, negative 1, negative 1 is going to result in 5, 2, 1, negative 6, and negative 2. And that's going to be 0. All right, so take a look at the B groups, see what you come up with for the B groups. All right. So those of you that have finished, are you coming up with these numbers? Okay, so again, for B1, everybody has a 1 in the first column, so that's always going to be 5. For B1, the second number is, I'm sorry, negative 1, so there should be a negative 1 there. So negative 1 for the B1 times the 1 here times the 2 here gives me negative 2. That's where that comes from. Okay, do you feel comfortable seeing how to get those numbers? All right, so how many B1s are part of this representation? 1, because if I add these up, I'm going to get 12 minus 4, which is 8. 8 divided by 8 is going to be 1 B1. And then when I add up for B2, how many are there going to be? 0. All right. Now for the E, what we want to remember is that it is doubly degenerate. So if we have one of them, it counts as 2 of our modes. Okay. So for E, our characters are 2, 0, negative 2, 0, 0. Oops, missed a spot. We all know that 0 multiplied by anything is just going to be 0. So the E's are nice because they tend to have zeros in them, and we can just ignore those. So the only things I have to multiply are the first and the third. So 2 times 5 times 1 is 10. And negative 2 times 1 from here times 1 from here gives me negative 2. So how many E's are part of this? 1. So it's going to end up being 8 over 8 is 1 E.
Can you say why we got zeros there?
Look at the character table.
Yeah.
Okay. So now we know that the vibrational modes are 2 A1s, a B1, and an E. Okay. And so I can tell you that your E is probably going to be 2 things that look a lot alike, but I'm just switching what atom. So if I'm looking down the center of the atom, so here's the bromine, and I've got chlorine, 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 chlorine. I could do this side goes out, so I'm going to draw the arrow moving out, and this side goes in. Or instead of going sideways, I could go up and down. So if you can figure out what those are, you can usually figure out what the E is. Because it's going to be the thing that it's like, oh, I'm just switching which atoms. Okay. That is harder to do when you have odd numbers because it looks weird on odd numbers. But on even numbers like 4, you can do this. Okay, so what is the B gonna be? Well, what's another way I could have 2 stretching out and 2 stretching in? Or 2 compressing in? Instead of doing side by side going out, what could I do? Opposites, right? So I could have this and this. So a B usually looks like the things that are right next to each other are doing opposite things all the way around. Okay, so not this, but this was reduce the representation. We did that. Then I might ask you, which are visible in IR spec and which are visible in Raman spec. So what am I going to do to answer that question? You got to look at your character table, got to look at those last 2 columns. Okay. The third column from the right or the second from the end is my linear combinations. Linear combinations are going to tell me which one. IR. Now, does it have to be something specific or can I look for anything labeled in that column?
The C, X, and Y.
The Z, X, and Y. So the R's don't tell us anything about IR spectroscopy, but I'm looking for Z, X, and Y. Okay, so is my A1 visible in the IR? Yes, the A1 is visible in the IR. Right, put an IR. Both of those are visible. All right, is the B1 visible in the IR? No. Is the E visible in the IR?
Yes.
Yes.
Wait, why is A2 visible?
It's not?
Oh, yep, just kidding.
Yeah, that's the 0. We don't have any. It's just the A1.
Okay, that's.
Okay, and then which are visible in the Raman? There anything at all in that column rather, tells us that it's visible in the Raman. We don't have to look for specific combinations. So is IR visible? I mean, is A1 visible? Yes, because there's something there. Is B1? Yeah, A2 is not, but B1 is. Yeah. And then the E, is that visible in Raman?
Oh.
Yeah. Okay, so that's putting all the pieces together.
So is this like a question you would ask someone? Rachel. Hello.
Hi, Rachel.
on there?
Well, when you watch it, I said, hey.
So kind of orbital might this be? P orbital. If there's something in the middle, that's just so I could stick axes out of them. So stick other toothpicks out of them. It's not supposed to mean anything. Just think of it as like the nucleus of the atom. Okay, so these are P orbitals. All right, then each basket has 2 of these. These are D orbitals. Now, this one has my axes shown, right? And the lobes are going in between those axes, right? Is that going to be, now we said before the yellow was going to be our Z on other things. So let's just say yellow is the Z. So this is lying in the XY axis. So is this going to be the XY orbital or the X squared minus Y squared? X squared.
What a great question. Absolute question.
So
How do you even tell?
the ones that have no squared are between the axes.
The ones that have no square are between the axes and
Yeah.
that they're on the axes. It's.
No, see, this is the axis here and here.
Oh.
Okay, so.
Yeah.
If I have the y-axis here and the x-axis here. So I'm looking down the z.
That is interesting.
This is gonna be x, y. Okay, so between equals x, z, x, y, and y, z. Those three. Okay, so in the next chapter, we're gonna talk about those being triply degenerate. They all look the same and they're all between the axes. And so they're all gonna behave the same when we start making molecular orbitals. Okay, now also looking down the x and the y. And I didn't have long enough toothpicks to do this in most cases, but let's see, this one, if we say this one is sitting on the axis instead of between the axes, that's the x squared minus y squared. Okay,
So mine is like what, the ZX?
yes,
So this is x squared minus y squared.
yes. Okay,
Gosh, that's.
so on the axes, it could be x squared minus y squared, or what do we call the one that goes up and down?
Z squared.
Z squared, and that's the one that looks like a p orbital, but it's got a donut. Okay, these are going to be doubly degenerate, so these will be labeled as T in the next chapter. These will be labeled as E in the next chapter. Are you hula hooping like a d orbital? One year for Halloween, I dressed up as a d orbital, but nobody got it because, you know, I wasn't teaching inorganic chemistry at the time. So, but I had like a little inflatable pool thing. Okay, we are going to think about a molecule. All right, a molecule that has the formula. Ah, here it is. I put it on the chair. There we go. MX3L3. Okay, so when I have an ion or a molecule that has a metal center and then it has ligands around it, we call that a metal complex. So this is a metal complex, or it says a complex, and it has this formula, MX3L3.
Wow.
So what I want you to do with the molecules that are in there, or with the modeling things that are in your basket, or drawing, or just mentally, what I want you to do is come up with 3 different arrangements that could be X3L3.
Yeah, we don't have different stuff.
Now, one of them, one possible one, does not have, I don't have the center for it, but it's possible that you could have, actually several of them, you could do it this way. It's possible to have ones that are flat. Okay, so every group came up with meridial. Did you guys come up with a second one?
It would have been the one where you have the green and white one on top and then 2 green, 2 white.
Okay, what about back here? Did you guys come up with a second one? Still working on it? Okay,
No, that's one. Oh,
so this one is if it's in a plane. This is the other one. Yeah, that's the second one. So the second 3-dimensional one is called spatial. All right, so next thing I'm going to ask you to do is point groups.
All right. I didn't see that.
let's go.
Because it outlines the face of one of the octahedrons. This one's flat.
This one would come up here.
Yeah. So like, that'd be C.
And then you could also have variations of this where like 3 of them are together or 2 are together and then 1. There's lots of variations of that. Remember, color matters when you're thinking about whether things change. If you go from one atom through the middle to the other side, does it change color? If it changes color, then there's no inversion center. Take the odd man out and point it up. And so since you have three atoms that are a different color than the other atoms, point all three atoms up. All right, so you can set that on the table. Okay, so this guy, let's start with this one. Meridial is called meridial because the like ligands are all on an axis, like you're going around the prime meridian of the Earth. So just like in planar things where we have cis and trans, in this case with three, we need more because there's more than just cis or trans possible. Facial is forming the face here.
Right.
And when early inorganic chemists were trying to figure out the shapes, they didn't really have the X-ray spectroscopy to figure out how things were going together. So they used group theory to figure out what was possible based on how many vibrations they saw and how many different isomers they got. So this isn't one that happens, but there was a large group of inorganic chemists that argued for a long time that they thought it was built in a plane rather than like this. So we don't really see the planar ones. But suppose we did this one. Okay, so this one is going to be C2B. And that one is C3B. So remember to take here, let me borrow. Take your odd man out, and since there's even numbers, they're both the odd man out. So I'm gonna take the center green one and point it up, or I could take the center white one and point it up. Okay, so that's gonna be your z-axis. And so I can turn it 180, and that's my highest rotation, right? Because if I turn it 90 degrees, then I'm changing color. So turning 180 makes it a C2. If I flip it upside down, I'm swapping green and white, so I can't flip it upside down. So it's in the C groups. If I do a horizontal mirror plane, I'm swapping white and green, but I do have those vertical planes. So that's C2V. In the C3V, I point all three green ones up. This becomes my Z-axis. And if I look down here, I've got a nice triangle here that I can rotate 1/3 of the way around. Okay. And then over here, I also have a C3, but because it's flat, I can flip it over. So it's in the D group. So D3, and do I have a horizontal mirror plane? If this is the Z-axis,
Z-axis is going towards us.
Z-axis is coming towards you. Because the plane of the board is, oops, so that's D3H. Okay, so we got our point groups. Okay, and then if it is known to be nonpolar, so we talked about what the point groups can tell us, what groups are going to be nonpolar, what groups are going to be polar.
You would expect the meridial one and facial one to be polar, and you expect the planar one to be non-polar.
Yeah, so the CN, C whatever number, that's polar, CNV is polar, and CS are polar. So anything that starts with C except for CI is polar, and all the others are non-polar. So all the D groups are non-polar. Okay. On the next two pages, we're not gonna have a chance to go through this, but I was gonna have you do this as a group, so I have 2 pages per group. Examples of kind of what we did with the 6, a 7, an 8, and a 9. I will put these up on the desk when I leave, so you can take pictures of the ones you don't have. But for each of them, you're gonna say, what is the point group? And if you look at number 7, that's platinum tetrachloride. We've done that one. Okay, so that was D4H. You find the character table, find what the order of that point group is, calculate degrees of freedom. What's the formula for degrees of freedom? 3N. How many vibrational modes? 3n minus 6,
Unless-
unless it's linear, then it's 5, and you need to know that for your homework assignment. And I will give you all of the total motions, so you don't have to find them. So in bold there, all of the irreps that are part of the total motions, you have to tell me which ones are translations, which ones are rotations, which ones are vibrations. All right, and then tell me which ones are visible in the IR and which ones are visible in the Raman. Okay, this is practice. It is not an assignment, but it is similar to what you might see on your quiz.
You explained the wrong again really quickly, how you know which one's the positive one.
So on your character table, you've got all of your characters in here.
Yeah.
This column is the linear column, and in there you're gonna see your Z and your X and your Y and your RZ and so forth. Okay, so this is where you look for IR. This one is where you look for Raman. If I've got Z squared here, then yes.
So Z squared, Y squared, and X squared in the location. X.
Anything at all in that column.
Oh, anything.
Yeah, so if I've got X, Y, if I've got Z squared minus X squared minus Y squared, anything at all. But this one is blank, so I would say that one's not.
Okay, gotcha.
Now I'm just making these up. This isn't actually C2B, so. But just anything at all in the fourth column, you can see it in the row. All right?
So do the topics get like a lot worse than this? I'm gonna say,
Say
I
no.
think that's gonna be.
Say this is not what I think you do.
You're all handling these topics. You're all doing okay.
That's
This is like the most.
Well, that's true. You haven't taken the quiz, but even though it's hard, you're doing it. This
Is it?
You know you're learning when you are struggling.
I looked at the homework, I didn't even know what the question was asked.
So I've been struggling for 4 years.
Yes, you learned so much.
It's like I don't know.
Yeah, Constanza. Yes. Yes.
Can we do a group quiz?
Yeah. Dr. Wilson said you.
So the reason I have 4 different questions is I tried that last time and they ended up doing worse because the people who actually were good at it didn't trust themselves and they second guessed themselves and people got answers wrong. Bye, Rachel.
Can I make some nice one?